Welcome to section 4.4, Profit, Cost, and Revenue. We're diving straight in today with example 1. So here we have a revenue and cost function given in this graph. And part A asks us to estimate the maximum profit and the quantity which maximizes the profit. Alright, so we know that profit, which really we normally use pi. Okay. This profit is the revenue, which is the total amount of money the company takes in, minus the cost of however much it takes to make said product. Okay. So the profit is going to be maximized when we are subtracting the least amount of money from the most amount of money. Alright, so we want a really big revenue and a really small cost, and that will help us get our largest profit. Alright, so I'm going to go ahead and make one of these a different color. Let's see here. So now we have this cost function in kind of a pink color, and the revenue function is in the original blue. Alright, so we know that we are making money anywhere that the revenue is higher than the cost. Alright, so in this area here, we are making money, so there is a profit. Alright, but we're asked to estimate the maximum profit. So where is the distance between the cost and the revenue functions the greatest in this section? Alright, well, it looks about where we have this line already marked for us, right about here. This looks like the greatest vertical distance between the cost and revenue functions. Alright, so our maximum profit then, it looks to occur around Q is equal to 140. Alright, so the profit at this 140 is going to be the revenue at 140. This is our revenue function, and we're given that the value is 80,000. So 80,000 minus the cost, which we're given as 60,000. So our estimated max profit is about $20,000. Okay? So part B asks, how do the marginal revenue and marginal cost compare at this value Q? So this Q is equal to 140. We want to examine the marginal revenue and the marginal cost. Remember, those are just the derivatives of the revenue and the cost, right? So we want to look at the slopes of the tangent lines. Let's go ahead and break out the ruler here. Alright, this is just an estimation, right? So we want the tangent line at Q is equal to 140 for our cost function. There we go. And same thing for our revenue function at Q is equal to 140. They look to be about the same, don't they? Alright, so marginal revenue looks to be equal to marginal cost at Q is equal to 140. Alright. So example 2 asks us to find the quantity which maximizes the profit if the total profit is given by this function here. Okay, so we know how to find maximums and minimums, right? We must first take the derivative. So pi prime of Q is 600 minus 8Q. And then what do we need to do? We need to set that derivative equal to 0, right? Set equal to 0. And then solve for q. So we have 8q is equal to 600. Divide by 8, we get q is equal to 75. This is one of our critical points. We have a polynomial function, which means we are defined everywhere, so we don't have any undefined points. But we do have this critical point where our derivative is 0. Okay. And we need to test, is this a maximum or a minimum? So I'm going to go ahead and use the second derivative test. So the second derivative of q, or of pi, is -8. So no matter what value of q I put in there, we're going to get -8 out of there, right? Our second derivative is a constant. Alright, but just for clarity, I'll go ahead and put in the second derivative of 75 is -8. So this is negative, which implies we are concave down, which tells us we have a local max. Alright. And now we just learned that in our first example, our marginal cost and our marginal revenue were very similar. Okay? They look to be about the same where we had the greatest profit. So we know that our profit function is our revenue function minus our cost function. Okay? And we're just going to make a little note that the derivative of our profit function, well, this is just the derivative of our revenue function minus the derivative of our cost function. And we have those fancy words for when we take the derivative of cost or revenue or profit, and that's, we put marginal in front of it, right? So this marginal profit is equal to the marginal revenue minus the marginal cost. Well, we typically, when we're trying to find a max or min, we set the derivative equal to 0 that we're trying to solve for. So if we set this equal to 0, our profit equal to 0, we have marginal revenue minus marginal cost. And if we move marginal cost to the left, we get marginal cost equals marginal revenue. And this is the same result we got from example 1, right? So it's just a few different ways to look at finding the max profit, okay? Let's go ahead and look at example 3. We're going to find the quantity which maximizes the profit if the total revenue and total cost are given by, here we're given two functions, so revenue and cost. We're also given some endpoints. Okay, remember when we're trying to find a global max, we also need to examine the endpoints of the function. Alright, so first let's go ahead and look at our marginal revenue. So our marginal revenue, well, that's the derivative of the revenue function, right? So this is 5 minus 0.003 times 2, we get 6, q. And marginal cost is the derivative of the cost function, which we just get 1.1. Alright, and we just learned that we could set these two equal to each other to find our max profit, right? Or to find our possible points for our max profit. So if we set marginal revenue equal to marginal cost, this is going to give us 5 minus 0.006q is equal to 1.1. so we go ahead and subtract 5 from both sides. We get negative 0.006 Q is equal to negative 3.9. And then we go ahead and divide by that negative 0.006 to get Q is equal to 650 units, right? But again, we need to know if this is a max or a min before we go ahead and call it. So we need to check to the left and to the right. We didn't actually come up with a margin or with a profit function here. We could, but we didn't come up with a profit function here. Instead, we need to examine the marginal revenue and the marginal cost. Okay, so we're going to check marginal revenue and marginal cost to the left and right of Q is equal to 650. Alright, so if we check to the left first, we're going to check Q is equal to 649. So if we look at the marginal revenue of 649, we get 5 minus 0.006 times 649. Alright, plug this into a calculator, we get 1.106. And the marginal cost of 649, well, that's just 1.1. It doesn't change at all, right? So in this case, our marginal revenue, this number here, is greater than our marginal cost by very, very, very little bit, right? But it's still greater. Alright, so now we need to look at the right-hand side. So Q is equal to 651. So this gives us marginal revenue of 651, which is 5 minus 0.006 times 651, and we get 1.094. And then the marginal cost of 651, well, that again doesn't change. It's still 1.1. So here, marginal revenue is now less than the marginal cost at 1.1. Okay, so I'm going to spell this out here in words for us. This means that to the left of Q is equal to 650, the revenue was, or I'm going to say is, or the revenue is increasing faster than the cost. But to the right of this point, Q is equal to 650, the revenue is increasing slower. This gives us a local max. Alright, so we may have found a local max, but we need to check if it's a global max. Alright, so we need to evaluate the profit at Q is equal to 650, our critical point, and also our profit at 0 and at 1000. Those were the end points of our function. So our profit at Q is equal to 0. Well, this is our revenue at 0 minus our cost at 0, which gives us negative 300. Right? These are the startup costs. If we remember correctly, these are our startup costs. So we haven't sold anything yet, but we've already spent money to get it up off the ground, right? Okay, so we're losing money there. There's actually negative profit. So then we'll look at the other endpoint, which is Q is equal to 1,000. So we have the revenue of 1,000 minus the cost of 1,000. Well, that gives us positive 600. Okay, so now we're making money. At least we have a positive profit number. But if we go ahead and look at Q is equal to 650, which is our critical point, we end up with the revenue of this 650 minus the cost of the 650, and we get 967.50. Alright, so Q is equal to 650 is a global max for our profit function. Okay, example 4. So at a price of $80 for a half-day trip, a whitewater rafting company attracts 300 customers. For every $5 decrease in the price, an additional 30 customers come. Assuming costs do not depend on the number of trips sold, what price should the company charge per trip to maximize the profit? Alright, so part A asks us to first find the demand equation. And then it specifies that the demand equation is the quantity as a function of the price. Okay, so our price is $80 currently, and the number of trips, which are given as Q, okay, the number of trips is 300 when the price is $80, okay, and the decrease in the price is constant. We're decreasing by $5 every time. So if the price is $75, so if we decrease by $5, I'll say this implies, well, we're going to gain 30 customers, so we'll have 330 customers. Okay? Since we have a constant change, we have a linear function. So constant change, that implies we have a linear function. And we know how to find an equation for a linear function. First, we need to find the slope. And we have 2 points right here. Okay? So, we have 300 minus 330 over 80 minus 75. Alright, then we get negative 30 over 5. So we end up with negative 6. And if we want units, this is actually going to be people per dollar. Alright, or customers maybe would be a better, customers per dollar. Alright, so if we have this function, which is the quantity as a function of price, so Q is equal to negative 6 times P, which is the price. So this is our Y equals MX, right? And we're missing V plus B, the Y-intercept, or in this case, our Q-intercept. Okay? So we need to find B. Well, we can do this by plugging in one of our points, okay? Here we have 3 unknowns, but we could plug in 2 of them up here, and then we could solve for B, okay? So, if Q is 300, then we have P as 80 plus B. So we get 300 is equal to negative 480 plus B. So we get B is equal to 780. All right, so our demand equation is Q is equal to -6 times the price plus 780. All right, so that is our demand equation. For part B, we are to express the revenue as a function of price. Okay, so our revenue, we know, is the price times the quantity. It's the total amount of money brought in by how many items are sold. Okay, so we know we found the equation for the quantity, for the demand, for Q, so we have P times -6P plus 780. If we go ahead and multiply this out, we get -6P squared plus 780P, again where P is the price. So here we have revenue as a function of price. Alright, so part C asks us to find the price which maximizes the revenue. So we found our revenue function. We have R of P is equal to our -6P squared plus 780P. And we need to maximize this, so we need to go ahead and take the derivative. So we'll get -12P plus 780. And we need to go ahead and set that equal to 0. -12P plus 780. So move the -12P over, and then go ahead and divide both sides by 12, so we get P is equal to 65. And this is a critical point, so we need to double check if this is a maximum. Alright, so we'll go ahead and take the second derivative, which is just -12. Alright, so the second derivative of 65 is going to also be -12, which is negative. So it's concave down. So this is a maximum. Okay, so $65 will maximize the revenue. Alright, and that is the end of example 4 and also the end of section 4.4 and also the end of chapter 4. So we're cutting the chapter a little bit short. Don't forget to take the comprehension quiz, and I'll see you at the start of chapter 5.